Imagine crafting a towering skyscraper without a strong foundation. At first, it looks perfect. Glass windows reflecting the sun, steel frames reaching for the sky. But one day, a small crack appears, then another, and before long, the entire structure begins to sway dangerously. This is what happens when software lacks a solid foundation. The code works until it doesn't. It becomes rigid, fragile, and impossible to scale. But what if there was a blueprint, a secret framework that could ensure your software remains strong, flexible, and scalable? Welcome to the world of solid principles. 5 powerful guidelines that transform ordinary code into well-structured, maintainable architecture. Let's discuss first principles. Single Responsibility Principle, SRP. The Single Responsibility Principle states that a class should have only one reason to change, meaning it should focus on a single responsibility. Imagine a chef in a restaurant who is not only cooking, but also cleaning, serving customers, and handling payments. It's overwhelming and inefficient. A better approach is to assign each task to a different person. Let the chef cook, the server serve, and the cashier handle payments. Now, let's look at an example in code. Consider an order service class that has methods for adding and removing items from an order, printing invoices. Here, order service has multiple responsibilities, handling orders and generating invoices. By mixing responsibilities, we make the class harder to maintain. Any changes to invoicing logic could unintentionally affect order management. To follow SRP, we should split these responsibilities. Order service handles order operations, adding, removing items. Invoice printer, responsible for printing invoices. This separation makes our code more modular, maintainable, and scalable. Next is Open-Closed Principle, or OCP. The Open-Closed Principle states that a class should be open for extension, but closed for modification. This means we should be able to add new functionality without altering existing code. Imagine you order a pizza. The chef starts by making the base from scratch, then adds the toppings, and finally bakes it. This approach takes time and introduces risk. If the base isn't cooked properly, the whole pizza is ruined. A better approach? Pre-make the base, then simply add toppings and bake. This makes the process more efficient and flexible while keeping the base intact. Now let's look at an example in code. Consider a discount calculator class with a method. Calculate discount type, amount. Right now, it supports only 2 discount types: percentage discount, fixed discount. What if we need to introduce a new discount type in the future? With our current approach, we'll have to modify the calculate discount method and add another else if condition. This violates the Open-Closed Principle because we're modifying existing code instead of extending it. To solve this, we can use polymorphism to extend functionality without modifying existing code. Step 1. Create an abstract discount class with a method applyAmount. Step 2. Extend this class for different discount types. Percentage discount. Implements apply for percentage-based discounts. Fixed discount implements apply for fixed amount discounts. Step 3. When a new discount type is needed, we create a new class instead of modifying existing code. It avoids modifying existing logic, reducing the risk of breaking the code, making the code scalable and maintainable. Next is Liskov Substitution Principle, or LSP. The Liskov Substitution Principle states that subclasses should behave like their parent class and be interchangeable without altering the program's correctness. Imagine you rent a car. You expect it to have a steering wheel, brakes, and an accelerator, basic features of any car, but instead, you're given a horse. Sure, it can move, but it doesn't behave like a car. You'd be disappointed because it violates your expectations. The solution? A car should always behave like a car, not like a horse. Now, let's look at how this applies in code. Consider an abstract bird class with a method fly. Now, let's say we create a subclass ostrich that extends bird. Ostriches can't fly, but since ostrich extends bird, it inherits the fly method, which breaks LSP because not all birds can fly. To follow Liskov Substitution Principle, we should restructure our design. Step 1. Instead of putting fly in the bird class, we create a separate interface called iFlyingBird. Step 2. Now only birds that can fly will implement this interface. Sparrow can fly, extends bird, and implements iFlyingBird. Ostrich cannot fly, only extends bird, without a fly method. Why is this better? It follows LSP arrow. Subclasses remain interchangeable with their parent class. It prevents incorrect behavior. Ostrich no longer has a fly method it can't use. It improves maintainability. The class structure is logical and predictable. Moving on, let's discuss the Interface Segregation Principle, ISP. The Interface Segregation Principle, ISP, states that an interface should contain only the methods that are relevant to a specific functionality. Imagine a gym coach who is also forced to train swimmers and sprinters all at once. This is overwhelming. He won't be able to manage everything effectively. A better approach is to have a gym coach for strength training, a swimming coach for swimmers, a sprinting coach for runners. Now let's see how this applies in code. Consider a large interface called All Operations that includes processing payments, printing invoices, sending email notifications. If a class only needs to process payments, it must implement all the methods, even if it doesn't need them. This violates ISP because classes should not be forced to implement irrelevant methods. A better approach is to split this large interface into smaller, more focused interfaces. iPayment Processor handles only payment processing. iInvoice Printer, responsible for printing invoices. iEmail Notifier deals with sending emails. Now, if a class only needs to process payments, it can implement iPayment Processor without worrying about the other methods. Why is this better? It follows ISP, ensuring that interfaces are small and focused. It allows flexibility so classes only implement what they need. It improves maintainability, making the system easier to extend without modifying existing code. Last but not least, let's talk about the Dependency Inversion Principle, DIP. The Dependency Inversion Principle, DIP, states that high-level classes should depend on abstractions, not concrete classes. Imagine your home has hardwired electrical appliances, TV, fridge, and computer, all directly connected to the wiring. Now, if you buy a new appliance, you'll have to redo the wiring, a tedious and inflexible process. A better approach? Install sockets instead. Now, you can plug in any appliance without modifying the wiring. Now, let's see how this applies in code. Consider a user report class that has a method generateReport and user repository field. Right now, user report depends directly on user repository, a concrete class, to fetch user data. If we change user repository or introduce a new data source, we have to modify user report, which violates DIP. A better approach is to create an iUser repository interface instead of directly using user repository and pass iUser repository into the user report constructor instead of hard-coding the dependency. Now, user report depends on an abstraction, iUser repository, instead of a concrete implementation, making it flexible and scalable. By following DIP, we reduce dependency on specific implementations, improve maintainability, make the system more adaptable to change. This principle helps keep our code loosely coupled, flexible, and future-proof. Thanks for watching.